Probability theory is the branch of mathematics concerned with probability, the analysis of random phenomena. The central objects of probability theory are random variables, stochastic processes, and events. Mathematical abstractions of non-deterministic events or measured quantities that may either be single occurrences or evolve over time in an apparently random fashion. It is not possible to predict precisely results of random events. However, if a sequence of individual events, such as coin flipping or the roll of dice, is influenced by other factors, such as friction, it will exhibit certain patterns, which can be studied and predicted. Two representative mathematical results describing such patterns are the law of large numbers and the central limit theorem. As a mathematical foundation for statistics, probability theory is essential to many human activities that involve quantitative analysis of large sets of data. A great discovery of 20th century physics was the probabilistic nature of physical phenomena at atomic scales, described in quantum mechanics. History. The mathematical theory of probability has its roots in attempts to analyze games of chance by Gerolamo Cardano in the 16th century, and by Pierre de Fermat and Blaise Pascal in the 17th century. Christian Huygens published a book on the subject in 1657, and in the 19th century a big work was done by Laplace in what can be considered today as the classic interpretation. Initially, probability theory mainly considered discrete events, and its methods were mainly combinatorial. Eventually, analytical considerations compelled the incorporation of continuous variables into the theory. This culminated in modern probability theory, on foundations laid by Andrei Nikolaevich Kolmogorov. Kolmogorov combined the notion of sample space, introduced by Richard von Mises, and measure theory and presented his axiom system for probability theory in 1933. Fairly quickly this became the mostly undisputed axiomatic basis for modern probability theory, but alternatives exist. In particular, the adoption of finite rather than countable additivity by Bruno de Finetti. Treatment. Most introductions to probability theory treat discrete probability distributions and continuous probability distributions separately. The more mathematically advanced measure theory-based treatment of probability covers both the discrete, the continuous, any mix of these two, and more. Motivation. Consider an experiment that can produce a number of outcomes. The set of all outcomes is called the sample space of the experiment. The power set of the sample space is formed by considering all different collections of possible results. For example, rolling an honest die produces one of 6 possible results. One collection of possible results corresponds to getting an odd number. Thus, the subset 1, 3, 5 is an element of the power set of the sample space of die rolls. These collections are called events. In this case, 1, 3, 5 is the event that the die falls on some odd number. If the results that actually occur fall in a given event, that event is said to have occurred. Probability is a way of assigning every event a value between 0 and 1, with the requirement that the event made up of all possible results be assigned a value of 1. To qualify as a probability distribution, the assignment of values must satisfy the requirement that if you look at a collection of mutually exclusive events, the probability that one of the events will occur is given by the sum of the probabilities of the individual events. The probability that any one of the events 1, 6, 3, or 2, 4 will occur is 5/6. This is the same as saying that the probability of event 1, 2, 3, 4, 6 is 5/6. This event encompasses the possibility of any number except 5 being rolled. The mutually exclusive event 5 has a probability of 1/6, and the event 1, 2, 3, 4, 5, 6 has a probability of 1, that is, absolute certainty. Discrete probability distributions. Discrete probability theory deals with events that occur in countable sample spaces. Examples: throwing dice, experiments with decks of cards, random walk, and tossing coins. Classical definition. Initially, the probability of an event to occur was defined as number of cases favorable for the event, over the number of total outcomes possible in an equiprobable sample space. See classical definition of probability. For example, if the event is occurrence of an even number when a die is rolled, the probability is given by, since 3 faces out of the 6 have even numbers and each face has the same probability of appearing. Modern definition. The modern definition starts with a finite or countable set called the sample space, which relates to the set of all possible outcomes in classical sense, denoted by. It is then assumed that for each element, an intrinsic probability value is attached, which satisfies the following properties. That is, the probability function f lies between 0 and 1 for every value of x in the sample space omega, and the sum of f over all values x in the sample space omega is equal to 1. An event is defined as any subset of the sample space. The probability of the event is defined as so: the probability of the entire sample space is 1, and the probability of the null event is 0. The function mapping a point in the sample space to the probability value is called a probability mass function, abbreviated as PMF. The modern definition does not try to answer how probability mass functions are obtained, instead it builds a theory that assumes their existence. Continuous probability distributions. Continuous probability theory deals with events that occur in a continuous sample space. Classical definition. The classical definition breaks down when confronted with the continuous case. See Bertrand's paradox. Modern definition. If the outcome space of a random variable x is the set of real numbers exists, defined by, that is, f returns the probability that x will be less than or equal to x, the CDF necessarily satisfies the following properties. Is a monotonically non-decreasing, right continuous function. If is absolutely continuous, i.e., its derivative exists and integrating the derivative gives us the CDF back again, then the random variable x is said to have a probability density function or PDF, or simply density for a set. The probability of the random variable x being an is in case the probability density function exists. This can be written as whereas the PDF exists only for continuous random variables, the CDF exists for all random variables that take values in. These concepts can be generalized for multidimensional cases on another continuous sample spaces. Measure-theoretic probability theory. The raison d'être of the measure-theoretic treatment of probability is that it unifies the discrete and the continuous cases, and makes the difference a question of which measure is used. Furthermore, it covers distributions that are neither discrete nor continuous nor mixtures of the two. An example of such distributions could be a mix of discrete and continuous distributions, for example, a random variable that is 0 with probability 1/2, and takes a random value from a normal distribution with probability 1/2. It can still be studied to some extent by considering it to have a PDF of where is the Dirac delta function. Other distributions may not even be a mix. For example, the Cantor distribution has no positive probability for any single point. Neither does it have a density. The modern approach to probability theory solves these problems using measure theory to define the probability space. Given any set, and a sigma algebra on it, a measure defined on is called a probability measure. If is the Borel sigma algebra on the set of real numbers, then there is a unique probability measure on for any CDF, and vice versa. The measure corresponding to a CDF is said to be induced by the CDF. The probability of a set in the sigma algebra is defined as where the integration is with respect to the measure induced by, along with providing better understanding and unification of discrete and continuous probabilities. Measure-theoretic treatment also allows us to work on probabilities outside, as in the theory of stochastic processes. For example, to study Brownian motion, probability is defined on a space of functions. Classical probability distributions. Certain random variables occur very often in probability theory because they well describe many natural or physical processes. Their distributions therefore have gained special importance in probability theory. Some fundamental discrete distributions are the discrete uniform, Bernoulli, binomial, negative binomial, Poisson and geometric distributions. Important continuous distributions include the continuous uniform, normal, exponential, gamma and beta distributions. Convergence of random variables. In probability theory, there are several notions of convergence for random variables. They are listed below in the order of strength, i.e., any subsequent notion of convergence in the list implies convergence according to all of the preceding notions. Weak convergence. A sequence of random variables converges weakly to the random variable if their respective cumulative distribution functions converge to the cumulative distribution function of wherever is continuous. Weak convergence is also called convergence in distribution. Most common shorthand notation. Convergence in probability. The sequence of random variables is said to converge towards the random variable in probability if for every epsilon greater than 0. Most common shorthand notation. Strong convergence. The sequence of random variables is said to converge towards the random variable strongly if. Strong convergence is also known as almost sure convergence. Most common shorthand notation. As the names indicate, weak convergence is weaker than strong convergence. In fact, strong convergence implies convergence in probability, and convergence in probability implies weak convergence. The reverse statements are not always true. Law of large numbers. Common intuition suggests that if a fair coin is tossed many times, then roughly half of the time it will turn up heads, and the other half it will turn up tails. Furthermore, the more often the coin is tossed, the more likely it should be that the ratio of the number of heads to the number of tails will approach unity. Modern probability theory provides a formal version of this intuitive idea, known as the law of large numbers. This law is remarkable because it is not assumed in the foundations of probability theory, but instead emerges from these foundations as a theorem, since it links theoretically derived probabilities to their actual frequency of occurrence in the real world. The law of large numbers is considered as a pillar in the history of statistical theory and has had widespread influence. The law of large numbers states that the sample average of a sequence of independent and identically distributed random variables converges towards their common expectation, provided that the expectation of is finite. It is in the different forms of convergence of random variables that separates the weak and the strong law of large numbers. It follows from the LLN that if an event of probability P is observed repeatedly during independent experiments, the ratio of the observed frequency of that event to the total number of repetitions converges towards P. For example, if are independent Bernoulli random variables taking values 1 with probability P and 0 with probability 1P, then for all I, so that converges to P almost surely. Central limit theorem. The central limit theorem is one of the great results of mathematics. It explains the ubiquitous occurrence of the normal distribution in nature. The theorem states that the average of many independent and identically distributed random variables with finite variance tends towards a normal distribution irrespective of the distribution followed by the original random variables. Formally, let be independent random variables with mean and variance, then the sequence of random variables converges in distribution to a standard normal random variable. Notice that for some classes of random variables the classic central limit theorem works rather fast. For example, the distributions with finite first, second and third moment from the exponential family. On the other hand, for some random variables of the heavy tail and fat tail variety, it works very slow or may not work at all. In such cases one may use the generalized central limit theorem.